All right, so if we remember, last class we wrote our implementation of the sorting guy, right? Insertion sort. So binary search or our dictionary search or a phone book search, however you want to think about it. This guy requires that our data be sorted initially. So we already got that part done, right? We got our data sorted. And I think we have on our code our proof of concept from that from last time. Have our unsorted list. We printed it, we called insertion sort, we printed it and saw it was sorted. Now remind me, why did I not have to say a list is equal to what's returned from insertion sort here? Why did this magically sort a list in its place? Why did I not have to return a value from my function? Go ahead. Pass by address, that's good enough. Pass by address, pass by reference. You could think about it like that. It's probably more important to be able to tell me what that means.
Oh, so it changes the value. Instead of change, it changes value in a list directly.
Okay, so when we pass something by address or pass it by reference, what we're really telling it is where it can find it up in memory. So any changes we make to that guy, that's the spray painting of my garage stuff, remember? If I tell you where my house is and you go there and you make changes, I'm going to find out about those changes when I get home. Same thing. We pass something by reference or pass something by address. Those are synonyms for each other. We're giving it the address where that place is in memory. So instead of handing them the list itself, we're handing them a piece of paper that says where they can find that list. Okay, and then when they go and make changes to that list, so inside here where we're doing all of our swapping, we're actually swapping stuff in the real list up in memory, which will be noticed externally. It has what's known as side effect. Does that make sense? All right. And then we also saw last time, I think I deleted it, but we wrote a simple little function that looked pretty similar to where we passed a number in, tried to change that number, and then saw that the number did not change externally. So we saw that numbers, integers, are passed by value as opposed by reference. Okay, makes sense. Numbers are little. Lists might be big. Okay, so just like in real life, I think I used the example of a quarter, right? If somebody asks you for a quarter, you don't give them the address where you last saw a quarter. It would be like I guess it would be funny, but in any case, it's Python is being intelligent by making those decisions for us. All right, so you want to make sure you're aware of what things are passed by value versus what things are passed by reference. And for us, if you wanted to make yourself a little cheat sheet or something like that, basically everything is passed by value except lists, and today we're going to introduce something called a dictionary. So lists and dictionaries for right now. Then we're going to add objects to that thing. Okay, so there's really a very small set of things that are passed by reference. Everything else is passed by value, but lists happen to be one of those things that are passed by reference. And this isn't just information you need to memorize about Python, because this idea goes into all of our other languages as well. When we are working with Java next semester, arrays, which is Java's name for a list, they're passed by reference as well. I guess technically Java does have something called, for a dictionary, it's called a hash map. Don't worry about that, but it's an object, would be passed by reference. All objects in Java are passed by reference, so it's not like you have to keep this stuff straight between languages. Pretty much all programming languages, all of our modern ones, deal with this stuff the same way. All right, just needs to be something that you're aware of. Okay, so now that we know we can go ahead and get a sorted list. In fact, you could even build that into binary search. You can make binary search work from the perspective of, I want to make sure that the list is sorted. So regardless of what you sent me, even if you sent me a sorted list, I'm going to go ahead and resort it just so I know it's sorted. You could potentially do that inside of binary search. The problem with that would be that means that every single time you search, you would be resorting the list, which could be expensive in terms of the amount of time. Even if you're not doing a whole lot of swapping things around, you're still doing all that checking. All right, so for us, we'll just assume that the list that gets passed in is already sorted. Now, last time we talked about having a generic algorithm for binary search. This is the idea of kind of calculating where's the middle of my current list. Okay, where's the middle of my current list? Going to that place and saying, is this the guy I'm looking for? Okay. If it is, return my answer. What did we say we're returning? We're returning the position or -1. So where we find it or -1. So either middle or -1 at the very end. All right, so we'll calculate middle. We'll say, is this the guy we're looking for? If yes, return the position of middle. If no, well, should it come before or should it come after that? Then we update our variables for the beginning and end and do the whole thing again. Over and over and over again. And when do we know we're done? A couple different scenarios. One is when we've found our answer, when middle is the value we're looking for. Or how else do we know that we've exhausted all solutions? All possible places to check. Because we definitely don't want an infinite loop here, right? We don't want to just keep checking forever and ever and ever. So we go back and look at our picture here. In some cases, we'll get a situation where begin and end are the same, right? But we want to make sure that end is never before begin. As soon as those guys cross over, we have a problem. Does that make sense? And we know we'll get the crossover because when we ask that question, should the value we're looking for come to the right or to the left of the current guy we're looking at, we update either begin or we update end, correct? And we might have a situation if begin and end are the same and we update begin, begin just crossed over end. Okay, so we went the wrong direction. All right, so we saw here we're going to need a couple of different variables, right? We're going to need a begin and end, keeping track of what is the left and right portion of the list that we're currently looking at. We're going to need a middle, which is going to be calculated each time through based on the current values of begin and end. And the value we're searching for is this dude that we're passing in. So we're searching for this guy in this list. We're going to go ahead and we're going to say begin is equal to the first legal position in list. We'll say that end is equal to, what's the last legal position in list? Length list -1, like that. All right, so now we're remembering the beginning and end of the current version of the list. So we kind of start the ball rolling by saying, okay, well, right now, as far as I know, I'm looking at the whole list. I'm looking at the whole dictionary. Okay, page 1 to the very last page. Now, as long as begin is less than or equal to end, because we do have a scenario where they can be the same, right? When we're kind of our last hope. Okay, so as long as begin is less than or equal to end, we're going to do some searching. Okay, so while begin less than or equal to end, we're going to do some stuff. And what are we going to do? Well, we're going to calculate the current position of middle. So I know I still have a place to check. So that's what we know inside here. If I'm inside the while loop, I know I have at least one place to check. Where am I going to check? Well, I'm going to check in the current middle. And what did we decide middle was last time? End plus begin divided by 2. Make sense? That calculates the current middle relative to the current begin and end of our list, where we understand that begin and end are going to be shifting potentially as we decide have to have which part of the list we might find the value in next. Okay, so end plus begin divided by 2. So we'll say middle is equal to end plus begin divided by 2. Okay, now we ask the question, is the guy I'm looking for at position middle in list? Now I know exactly where I should be looking next, right? So I ask the question, if list at position middle is equivalent to the value I was searching for, And we decided that this version of binary search that we're writing, instead of writing one that returns true or false whether or not it's found, we're writing one that returns the position where it was located, or -1 if it was not found. Okay? So if I found the value I'm searching for at position middle, I want to go ahead and return middle. Make sense? Otherwise, if I didn't find it there, now tell me, do I need an else here? It's not wrong to put an else here, but do I need an else here? Or can I just write some more logic? Why is it okay for me to now start asking the question, which half of the list is the value potentially in? Nailed it. Why is it okay for me to ask this question here? Again, notice that it's not indented under the if, so it doesn't belong to the if, rather than do it inside of an else like this. Doing it inside the else is not incorrect. So if that makes more sense to you, that's completely fine. In fact, we might even write it that way. I'm more just kind of pointing out in a specific example. Why is it okay for me to write the logic that would ultimately ask that question there instead of inside of an else? What does that dude do? What are the consequences of that line, return middle? Don't overthink it. A little bit more than that. Yeah, it ends this. Function's done. We don't get to this line. We don't get to a line after the while loop. The thing you're thinking about is break. Okay, break gets us out of the loop. Return makes a function end. The whole do not pass go, do not collect $200 thing. We're done. Okay, we've been killed off. We will never get to any other line inside this function, let alone the very next one. Okay? So I sometimes think about this kind of like a minefield. You're kind of stepping around in here, you're hitting if statements, and if one didn't go off, then you're still going. All right? Now, having said that, even though we could certainly write this code here because we know that this is effectively a trap, right? If we fall into that trap, we will be returning middle, which will make the method end, make the function end. So even though we can look at that and say, yeah, that makes sense, it's still not incorrect. And it might even structurally look better if we put an else in here and just write it this way. So we'll calculate middle. We'll ask the question, hey, if I found the guy I'm looking for, let's go ahead and return where I found him. Otherwise, let's do something else. That make sense? So this structurally gives us that if-else, maybe a little cleaner, but it's not incorrect to write it the other way because of the consequence of what return does. It makes a function immediately end. We don't do any more lines inside that function with a return. Okay, as opposed to break, which gets us out of the most local loop. We have one more keyword that we discussed. What was the other one? So we have return, we have break, and then we have a third one. That doesn't apply to anything we're doing right now, but I figure I'll bring it up just as a review. Continue. What does continue do? Reset it or it goes back or something. Okay? Go ahead.
You skip to the next iteration of the loop.
Yeah, no matter where we are in the current loop, because you might have more logic after the continue statement that you just said, look, I'd be wasting my time going and doing that additional logic. So instead, at this point, I've decided that this pass through the loop is a waste of time. I just want to kind of zip ahead and go to the next iteration through the loop. So what continue says is, we have our counter for our loop. If it's currently at 3, go ahead and move it to 4 and start this loop again. Immediately. Don't do any more logic. So we're kind of short-circuiting the loop to save ourselves some time because we know it might be a waste of time doing something later on. Or we might also know that I know enough right now to know that whatever's below me here is destructive. So I don't want to do it. So instead, I'm going to skip to the next one and move on with life. Okay, so it doesn't necessarily mean it's a waste of time. It might mean just you don't want to do it for whatever reason. Okay, so continue skips an iteration of a loop, just moves on to the next iteration through that loop. So we're still in the loop, we just skipped the rest of this current pass through the loop. Break gets us out of that loop. Return gets us out of the function. That make sense? Okay, and these are just tools that we can use under circumstances where they might be beneficial. All right. So if I found the guy I'm looking for, we're done. Return his position. Middle is the position where I found him. That's what we return there, right? So the value was in the list at position middle. That's what we asked here. Is the list at position middle equivalent to the value I'm searching for? If so, return the position where I found him. That make sense? Okay. Otherwise, we got to figure out should the value, I didn't find it yet, but I might still be good. Is the value I'm looking for to the left or to the right of my current value at middle? Well, it would be to the left if it's less than the value at middle, right? So if list, well, let's do this thing. If val is less than list at position middle, if that's a true statement, that means if it exists in my list at all, it's to the left of it, of where I currently am. So what I want to do is I want to update my version of end. Because right now, begin and end are here, middle is here. If I know the value I'm searching for is over on this half, let's just shift end all the way over here to be middle minus 1. Because I'm just going to focus on this part of the list. And we'll loop back up and do this whole process again of calculating middle, searching, blah, blah, blah. Okay, so if I know it comes to the left, we'll say end is equal to middle minus 1. Else, if it's not to the left, it must be to the right. And if it's to the right, then what are we going to update? We're going to update begin. So begin becomes middle plus 1. Because the next time through, we're only going to focus on the right half of the list. Make sense? So begin is equal to middle plus 1. Then we'll naturally loop back up. We will recalculate middle. Middle is being calculated in terms of the current values of end and begin, which we updated here. We definitely, if we're still in this loop, we updated end or begin. Not both, but one of them. Okay, depending on where our value, where is the most logical place to look for our value next. Okay, so we'll update middle here. Now keep in mind, we're only going to come back into this loop though, as long as begin is still less than or equal to end. As soon as these guys overlap each other, we've run out of steam. Not worth looking anymore, right? So what we do way down here at the beginning, at the bottom, and make sure you indent. So now we're equal to the while loop. So we're after the while loop is concluded. This is not a portion of the while loop. It's not a member of the while loop. We'll go ahead and return a negative 1. If I survive through all of this, never actually returning a position, and I continue to update where I'm looking at in the list, and I finally naturally end this while loop because I've run out of places to search, what I've been told to do is return a negative 1. I didn't find it. That make sense? Okay. So let's go ahead and we'll run our insertion sort here. Just so I'm going to actually run this real quick. once so I have my sorted list, even though it's a pretty short list and I don't have to really worry about it too much. I'm old. So there's my sorted list. And now we know, so let's go ahead and let's initially look for a 15. Okay, so we should find a 15 at 0, 1 at bucket 2. That's what that guy should give us, is a 2 for a 15, right? All right, so we'll go ahead and we'll take out these couple of prints. Those are just our evidence that it was working, right? And we'll go ahead and we're going to print the result of binary search. Binary search takes 2 parameters. The value we're searching for, we decided it was going to be a 15. And the list in which we're searching. And we're going to search inside of a list, keeping in mind that a list has now been sorted. So we're passing it a sorted list. Okay? And we're expected to get a, for 15, 0, 1, 2 out of this guy. Oh, yeah. I mentioned this last class, so I did this on purpose. When I do a normal divide by 2 here, this does floating point numbers, right? The double divide sign gives us the truncated version of our integer. Does that make sense? Because middle is going to be an index. What I just asked for there is like, give me bucket 2.5 of my list. He wasn't so happy about that. But the double divide symbol says divide by 2, truncated. This is integer division. Okay, so there's our 2. Okay, found the 15 there. All right, now let's go and let's search for a 3, and we should see a 0. There's our 0. Let's search for a 74. So 74 is going to be interesting. So we think about it, this is going to be 0, 1, 2, 3, 4, or 5. Now, depending on how you calculate middle, well, it's actually not depending on how you calculate middle, it's how you treat end. Is end the last legal position, or is it one past the last legal position? For us, it's the last legal position. So middle initially is going to be end plus begin, so this is 0, 1, 2, 3, 4, 5. 5 plus 0 divided by 2, so that's going to be bucket 2. This is our initial middle, right? Didn't find it there. Then we set begin to here. So begin is 3, end is 5. 5 plus 3 is 8, divided by 2 is 4. So we'll find it there. So in this particular case, because of the way we're doing our math, 74 should be found at bucket 4 as opposed to bucket 5. That make sense? Now, this just has to do with how we calculate middle. If we chose to do middle differently, well, like I said, actually, if we made end be 1 greater than it was, then we'd get a different middle. But we'd still check all the middles. You just want to make sure you're always consistent. And that's why in the homework assignment, it wasn't, I said return a position where val is found. Because with a binary search, you can't guarantee it's the first or the last position where it's found. It's the first time you stumbled upon it, but depending on how you were jumping within halves, it might not be the first occurrence. Does that make sense? So we'll go ahead and run this. What am I even doing right now? We're looking for a 74 now. Okay, and the 74 should be at bucket 4 based on the way our code is currently written. There's our 4. Okay, and then let's just search for an 82 and make sure that our loop actually does finally come to a natural conclusion. Because one risk you do have with binary search, something that's kind of a common mistake, is you end up writing an infinite loop, where you just continue to look at the same place over and over and over again because you never actually create a Boolean expression that fails this. And kind of the common here, let me run this real quick and I'll show you. I think I saved, right? Yep. Okay, so the common mistake that gets made with binary search is somebody might do something like not equal to end. So when they flip-flop each other, yeah, they're not equal to each other. We're still good. But also not equal to end also skips when you have an even number of characters, even number of buckets when they're the same for comparing them. So you've actually hurt yourself twice. You've taken away one last place to check, the final place to check, and then you also never escape. Does that make sense? Yeah. And sometimes you'll eventually get a crash as you update stuff because you'll end up getting a negative value for your middle, depending on where you were in the list. If n gets sufficiently right, n plus, no, you would never get a negative the way we're calculating middle. So it would just be an infinite loop. Okay, so that is a reasonable solution to binary search. Questions about that guy? Okay, so I'll go ahead and put this up on Slack. Let's see, where is 200? Okay. All right, so now what we want to introduce is we're kind of getting close, and actually, so I don't forget. The last chapter we read in the book was what? We have not read lists and dictionaries yet, right? We've read up through strings. Is that accurate? Okay. So we've already introduced lists here to you. So you can read through this if you want. In fact, I may have even had assigned lists, the reading for a list at some point. I don't remember, but go through lists. You might just skim this since you've already been introduced to them. But it does give you a couple of things like slicing out pieces of lists, that kind of stuff, things that might be handy. So go through that stuff, and then we talked about sorting lists, and then you'll find out that there's actually a built-in function for sorting lists, but why use that when you just write our own? Right? That's why I always had that caveat. You can only use stuff that I've introduced in class because there's almost always built-in stuff for half this stuff, or for a lot of the stuff, I guess. Okay, so what we're going to start talking about right now is this idea of a dictionary. And this is in our ramp up to classes. Now, and I'll just give you a little foreshadowing for this, and almost like a jump back to earlier in the semester when we kind of discussed this exact same topic. When we talked about the transition from a procedural language to an object-oriented language, we talked about C to C++. Remember that? Well, you might not completely remember, but you sort of kind of fuzzily recall that discussion. Okay? So when we talked about C being a procedural language, and we kind of talked about the difference between procedural and object-oriented languages, we had the pile of wires version of the telephone versus the thing that actually looks like a telephone. All right. So we said, what are the weaknesses with C? And it wasn't necessarily thought to be a weakness at first, but as we started solving more and more complex problems, we started seeing little issues with C. And C had this, I think I in the slide, I had something like, C supported variables, it supported arrays, so it supported lists. It supported this thing called structs. Okay, and a struct is a collection of name value pairs. Okay, but they don't necessarily all have to be the same type. You can have a person's name and their age and their weight and all sorts of stuff like that. Okay, they don't have to be all the same kinds of values, where lists hold all the same kinds of values. Makes sense? It's a list of numbers or a list of strings, that kind of thing. All right, so when we talked about when we moved to C++, well, we said one of the weaknesses with a struct in C was that you couldn't have functions as part of the struct. So structs were great for holding a whole bunch of information under a single variable name. Okay, so we could have a person struct that had a person's first name, a person's last name, their age, their phone number, a bunch of different pieces of information, and we could ask that struct, we could say person.first name, person.last name, person.age, that kind of stuff, to extract those individual pieces of information. And that was great, because that's beneficial. And that's almost like that precursor to objects. But what a struct didn't let us accomplish is it didn't let a person do anything. It didn't allow us to have functions associated with them. Okay, and we kind of showed that as an example. So now we're fast forwarding all these years, and if you kind of remember, as we went to from C++ to Java, we got rid of structs. And then we had that discussion that Java erroneously said, oh, well, isn't a class and a struct the same thing? So isn't a class that doesn't have methods, doesn't have functions in it, actually just a struct? Only sort of, because I said that structs were passed by value by default, whereas objects, classes, are passed by reference, by address. So even though you could functionally pull off a struct with a class without methods, it doesn't always behave identically. Okay, so don't worry about how much you recall of that. I'm just kind of, that's a throwback to something from 25 years ago, right? That discussion. Well, now we're about to have that discussion again. In Python, Python's version of structs is something called a dictionary. Okay? It's a mapping of name-value pairs. They're kind of like lists. Sort of. Okay? They're sort of like lists. Except what we do is we index into the list. Instead of bucket 3 or bucket 4, it's bucket first name. And then we can give it a value. All right, so let's start off by looking at this, and I'll just kind of bring up here. Here's our, inside of our code here. There's different ways. There's a couple of constructors for building a struct. I typically don't use this guy. I typically just set my structs directly, so I'll kind of show you. Okay, so now for a dictionary, we've seen that an empty list is open, close, square brackets, right? That's a list with nothing in it, and we can start appending stuff to that list if we want. A empty dictionary, so we'll call this guy person, is going to be an empty dictionary. Okay, pretty sure this is the syntax in Python 3. I guess we'll see in a second. Then I'm going to say person at bucket fname is equal to Mike. Person at bucket lname is equal to Lippmann. Person at bucket age is equal to 23. That ship has sailed. Okay, and then we're going to go ahead and we'll just print out person for the moment. Okay, so we started person off as an empty dictionary, and then we started setting certain buckets of person equal to values. So we have bucket fname is equal to the string Mike, bucket lname is equal to string Lippmann, bucket age is equal to the integer 23. So a bunch of name value pairs. Go ahead and run this and make sure the syntax is good. Yep, we're fine. All right, so this shows us a representation of what a dictionary looks like. Okay. Now, does this particular syntax we see here look like anything to any of you? Any format you've seen before? Not in this class necessarily. This is more of, I'm trying to see if anybody has seen something related to programming external to this class. How many of you have heard of JSON? JSON? Do you know what it is? Just a thing you've heard of, right? Okay. So these come down to this idea of data representation languages. And if you do the hackathon, I think you'll see that this stuff is very much used with working with third-party APIs and things like that. By the way, if you have not let Professor Josh Locklear know that you are going to the hackathon, do that as soon as possible because we're going to start putting teams together. I think the actual hackathon is April 8th, right? 12 hours on Saturday, April 8th, and then there's a warm-up for it where we do I'm going to be doing like a 4-hour thing on April 4th, which I think is a Tuesday.
Show up to a thing
For which?
for your
Well, I think he wants you to sign up for that as well to make sure we have enough. We pick a room that's good enough. I think we're planning on this room, but if you have enough people who want to do it, we'll go into a bigger room. But we're going to be doing a Android and an iOS simple app in those 4 hours that use a third-party API that will take advantage of JSON and this kind of stuff. So you'll kind of get a tiny little crash course on what the world of writing a mobile app talking to third-party stuff looks like. Just enough to be dangerous. Okay, because then what we're going to do is we're going to put together teams for the actual hackathon where there'll be a couple of seniors on a team with a couple of freshmen and sophomores. So the freshmen and sophomores who don't have a lot of experience can learn stuff. So no matter where you think your current skill set is, you will gain a lot. We're talking like a year's worth of knowledge in 12 hours coming to this, something like that. So I would highly, highly, highly encourage you to show up to that. It's really a pretty big deal. To the point where I'm not even going to give you extra credit to go. You're only hurting yourself if you don't go to the thing. Okay, it's that important. So we have something called JSON, and we also have something else called XML. I'm sure probably more of you have seen the 3 letters next to each other, XML, before. Maybe you don't know what that is either, but you've seen that, right? XML is older. It's been around longer. Okay, so these are data representation languages. Now, many of you have heard of HTML, right? You all worked with HTML in 150, at least a little bit. Kind of saw what that looked like. So HTML looked like a whole bunch of tags, right? Less than signs and greater than signs with words in the middle. Remember all that stuff? HTML was the influence for XML. So, and actually now it's like a reverse thing where you can implement the HTML language using XML. So XML is a tool for writing tag-based data representation languages. And what I mean by data representation languages is exactly what we're seeing here. We have a comma-delimited list of name-value pairs. Here's the variable name. Here's the variable value. Here's the variable name. Here's the variable value. And they have colons in between them. This is JSON syntax that we're seeing right here. This is how JSON represents its data. Okay? JSON also represents collections, which we don't have in here yet. But point is that what we're seeing here is JSON syntax, as opposed to maybe the XML syntax would be, an opening person tag, a closing person tag, an opening F name tag, a closing F name tag with Mike in the middle, an opening L name tag, a closing L name tag with Lippman in the middle, an opening age tag, a closing age tag with 23 in the middle. That make sense? A lot more verbose, but it's all just text. Not that big of a deal. But these languages, historically XML and much more recently JSON, is the data representation languages that third-party APIs use to send data to your program. So when you make a request to a database for some information, it sends you that information packaged up as a JSON string. That way you can then pull out the pieces of it that you wanted. Okay? So all this stuff is related to real world stuff that's happening today. Okay. So we have a little dictionary here. Person F name, Mike, L name, Littman, age 23. We printed it out. Now what we want to do, and this is kind of like a struct. On the surface, they look very similar. What we want to do now is we want to pass our dictionary into a function, try to change the value of that dictionary, and then look if it actually changed, telling us whether or not this guy was passed by value or passed by reference. I'm telling you that historically structs were passed by value, which means that we should not see the change. Okay, so we'll define a change dictionary function. This guy will take a dictionary as a parameter, and we'll go ahead and say dict at bucket f name is equal to Larry. Okay, nothing else. That's it. We'll pass it a dictionary. We'll try to change some value of that dictionary, and then we're going to print that dictionary back out here and see if that change actually was permanent. Okay, so we'll call change dictionary. We'll go ahead and pass it our person. Then we'll print out person. And if it still says Mike for person, what does that tell us about how dictionaries are passed to functions? So when I print out person again here, if it still says Mike, what does that mean about how dictionaries are passed to functions? Are they passed by value or are they passed by address? It means they're passed by address if it still says Mike. Okay, other way around. If it still says Mike, if I pass the address to this guy and I change it here from Mike to Larry, because I pass it the address, that's a permanent change. That's like me giving the address to my house and you go in and spray painting my door. When I get home, I'm going to see it. It's permanent. I am not going to get home and see a clean garage door. I'm going to see a garage door with paint on it. I will not see a struct that still has Mike in there. I will now see one that has Larry in there. So if it's passed by address, if when I take person and I pass it in here, if it was passed by address, when I change F name on this guy, that's a permanent global change. And when I print it out here after this call, I should see Larry if it was passed by address. If it was passed by value, that means I handed in a copy here. I changed that copy's F name value or variable to Larry, having no impact on the original, which means that when I print it out here, it'll still say Mike. That's passed by value. Okay, so let's see how this guy acts. It says Larry, which tells us that these guys work differently than structs. These guys work like lists. Okay? So whenever I pass one of these guys to a function and I make a change to it in that function, that's a permanent global change. That makes sense? Similarly, let's do this. What I'm going to do here, just to clean things up a little bit, I'm actually going to delete a lot of our code up here because we're starting to transition towards having this idea of objects. We're going to have separate files for things and stuff like that. All right. So what I'm going to do up top here is I'm going to create a dictionary called people. Okay. And people is going to actually contain a collection of people where each each person in this is going to have a first name, a last name, and an age. Okay? So, I'm sorry, people is not actually a dictionary. People is a list. People's a list. It's a list of dictionaries. So what I will do is I will append to people a first name, a last name, and an age in the form of a dictionary. So let me show you this. Where's this guy here? So this is def add person. This guy will take an F name, an L name, and an age. We're going to go ahead and build a dictionary out of that F name, L name, and age. Okay, so we'll effectively do what I did right here. Except I'm going to, instead of setting it to Mike, I'm setting it to F name. Instead of Lippman, L name. Instead of 23 is age. Okay, so I'm building a brand new dictionary. I'm filling that dictionary up with some stuff. There are constructors for dictionaries where you can build them in less lines of code than this, but for right now, I like it like this. So if I were to print out person here, it's going to print out our little JSON looking string that looks like the collection for person. Then what I'm going to do is I'm going to say people dot append person. Okay? So people is this list up here. And it's a globally available list. I defined it at the very top. So that means everything in here has access to this variable. The scope of that variable is the entire file as far as we're concerned. So this function has access to people because it's going to look locally first here. It's going to say, do I have any variables here named people? No. Is there any variable that I've defined as part of this function named people? No. I'm going to look the next layer up, which is this guy up here, the global scope, and say, ah, there's a people. And we're going to append to that list the person we just built. So I'll go ahead and I'm going to print out people right here. Then we'll go ahead and add a person. Okay, so there's the 3 pieces of information for my person. It should build a new dictionary, ultimately add that to my list, and then I'll go ahead and print out people again. So now we see that our list contains one element, and that one element is a dictionary. So that's a lot bigger type of thing than we've stored up to this point, right? Up to this point, we've held like lists of numbers. Now we have lists of dictionaries. Make some sense? All right, so no programming assignment for Wednesday, but you will have one on due on Friday. But for Wednesday, read that chapter in the book on lists and dictionaries. At least skim through the list part of it, but definitely read and do all the things for dictionaries. Sound good? All right, I will see everybody on Wednesday.